All right. How's everyone doing? Hanging in there? I'm not even wearing proper shirts for you guys anymore. They just literally, I'm reduced to t-shirts here at the end of the semester. They're not even trying to put on airs at this juncture. So I hope that doesn't reflect in your evaluations. By the way, P.S. Go through, complete those, not just for my class, for all your grad classes. Those should be in your inbox. Make sure that you go through and fill those out. Again, it's embarrassing when we've got classes of 8 graduate students and can't get everybody to fill out an evaluation. Those do end up being important and things like that. So make sure that you do take some time, jump on there, and fill that out. Something popped in my inbox. It looked like a couple of you had gone through and completed those already. Like, I don't know who, it doesn't tell us anything like that, but there were a couple of people who completed. So thank you if you've already done that. But if you haven't, take just a couple of seconds to go through and jump on there, complete those evals, because that's going to be helpful for us with stuff. Okay. Other thing, wanted to see, so we've got problem set 6 is going to be due Friday at noon, like sort of usual. Questions on, and I've been back and forth with people on the problem set, fielding a couple questions. Looks like people are generally on the right, in the right direction. But any questions that I can field? Brittany, you had sent me something. I was scrambling trying to get stuff to today for class. I didn't have a chance to look at your question closely. What were you having difficulty with? Oh, you're muted.
Sorry, I'm at I'm in a library, but the only question I had, and I kind of figured it out, was just like providing the justification for like the formula that we used when we were calculating effect sizes. But I figured it out. It's just to explain like why we chose what we did, right?
Yep. That's all we're doing there, right? And this is always the crux with our effect sizes, right? It's not like a t-test where you're like, oh, everybody's calculating t-test the same way. Depending on what you choose as your standardizer, that can start to have a big difference on what the point estimate of your effect looks like. And so just wanting to go through and make sure that you have considered that carefully and have a good reason for choosing whatever standardizer you chose for that, right? So the big thing here is generally going to be thinking about homogeneity of variance, violations of homogeneity of variance. Do I see that I have differences across my individual levels of my IV? And particularly if I have an unbalanced design, we start to wonder if just taking that mean squared error term is going to be a good representation of the variability, right? So depending if I'm running contrasts, what groups are in there, whether or not I have violations of homogeneity of variance, whether or not I have different sized cells, all that starts to come into play, and thinking about, do I just pull that mean squared error? Because mean squared error is just going to be the pooled variance of the entire design, but that might not always be a good option. So just going through and considering that. And if you're struggling with that, let me know. It's kind of can be tricky to wrap your head around, but if you're running into roadblocks, let me know. Other questions?
Was that for the last question? That information?
Brittany, what question was that? Is that the last question? Yeah. Looks like that was the last one. Okay.
I had also another quick question, and I know that you had said this before, but I was blanking. What are the implications of having a large effect size when you fail to reject the null?
Yeah, someone help us out. Like, what does that generally sound like? If I've got a decent sized effect, but I still fail to reject the null, right? I'm still, my point estimate of my effect size is pretty large, right? But I'm still not finding strong evidence for an effect based on my hypotheses test. What's generally going on there? What do you think, Rachel?
I'm not sure. I know that I wrote in my last one something about sample size.
Yeah. That's why I was picking on you, because you were exactly right. Okay.
Oh,
If I've got a pretty massive effect, right? So the difference between my groups is pretty large, but I still don't have evidence to detect that effect. It probably means that I have an underpowered study. Even if we're looking at a large effect, right? Even if I'm looking for fairly large effects in my literature and I have cell sizes like 10 or 15 or something like that, that's still a super, super underpowered study, right? And so there's a couple of different ways we could think about this. One, we could say, well, my point estimate, the effect that I'm seeing in my data is quite large, but I'm still not finding evidence for this. Which means I've got probably have a really small sample size, which means I really don't have much power. And so one conclusion we could make is saying, boy, based on the point estimate effect, it looks like we might be looking at a pretty sizable population effect here. I just don't have enough people to say with any sort of determination whether or not we have evidence for it, just because I'm limited with a really small sample. Okay. Now, the other thing that could happen, what else could happen? Let's say in my sample size of 20, I'm finding a large effect. Let's say I bump that sample up to 60, 70. What else could happen to that effect size? Is there anything to say that effect size, that my point estimate of the effect is going to be the exact same if I increased my sample? No, right? What I might find if I actually get, we talked about how with really small samples, we can sometimes get inflated effect sizes, particularly if I've got values that are kind of hanging way out on the margins. If I've got a sample size of 10 and someone just has I have one person who has a really high score, that can start dragging that mean out and make it look like there's a huge difference. If I start collecting more and more people, we actually see a shrinkage of that effect size because it's just getting closer and closer to the actual level. Now, that's not to say that's always the way it's going to happen. Sometimes maybe my point estimate of my effect in my sample size of 10 is actually spot on, and it's going to be pretty close to what I'm seeing if I were to have a larger sample. I just don't know, right? And so when you're thinking about this, right, a lot of these, I'm intentionally giving you a lot of ambiguous problems because easy problems are easy to say, yeah, if there's a massive effect, I don't have to worry about it a whole lot. But with our stuff, the types of research that we do, we often are working with small samples and getting stuff that's kind of ambiguous, right? And so if I've got a large effect, but I really got a limited sample, and so my hypothesis test is giving me limited evidence for sort of whatever it is that I'm looking at, but my point estimate on effect size is pretty big. Am I just going to look at that p-value, see that it hasn't hit 0.05 and just sort of wipe that off the board and say nothing to see here and move on? Probably not. That's probably not a good idea. I might cautiously say, looks like this study was underpowered because I didn't have too many people. Like I've got an objectively really small sample, right? Basically, these data don't tell me much of anything about anything, right? They're hugely inconclusive. But what I am getting is a point estimate that's of my effect size that looks like it's of reasonable size, right? And so this might be worth pursuing moving forward, given that it looks like there might be something there to take a look at, right? But right now, at the end of the day, our data is fairly inconclusive.
hey Josh, sorry.
Yeah.
Can I let Erica in?
Whoops, I'm sorry. Yeah, Hey Erica, that was some intensive relational aggression. Just like sort of making you sit out in the waiting room and not letting you. And I apologize for that. All right, but Natalie, does that help sort of clarify some stuff? Okay, and I don't know. I've done this, and I have a paper where we had not enough people to actually say much of anything, and so I made the argument. I'm like, look, so in this data, we don't have many people, and so what I'm going to do is I'm going to work primarily on effect sizes and sort of make my primary interpretation of that instead of my hypothesis testing because we just don't have enough people to say conclusively. So I'm going to run my hypotheses test, but primarily what I'm going to focus on is effect sizes, right? and apparently I've made a compelling argument enough that sort of that got published, right? Now, if I was reviewing the paper, I would say, well, fine, fair enough. But we also know that those estimates of effect size are super unstable with those with that small a sample, right? And if I would have calculated confidence intervals around those effect sizes, I would say, well, there's either nothing or something here. So, and all of that's reasonable, right? And so I probably got away with something there. I mean, it is an argument. It's not necessarily a strong argument, right? Without replication, and sort of if we were to do this with appropriate size sample to say, yeah, it looks like these point estimates of effect are sort of reasonable, right? So just wanting you to go through and take, and this is why, a lot of this applied stuff starts to become more tricky than just decision rules and saying, yeah, I have an effect. No, I don't have an effect. Want to take this all into consideration because it's really going to help you with your research, evaluating other people's research to say, okay, here's what we can say. Here's what we can't say. Here's sort of arguments that you say, oh, maybe we put some stock in this, but the drawback is I actually don't know with any degree of confidence that should whatever point estimate that they brought up here is reasonable. And so then using all that information to make an informed decision on whether or not you're convinced or not convinced on whether or not someone's found anything. Okay. So that was a lot, but that's kind of the idea. Just recognizing how our tests work. And the things that start to limit them, and sort of using our effect sizes and other stuff as maybe a supplement, and kind of integrating that all together to make decisions on how we're going to proceed with stuff. Cool. All right. Any other questions on the set? Okay. Talked with CJ today. He picked up a key for this set. This happens a lot. So my concern is with this. This is a big set. There's a lot of stuff to go through and integrate in all of this. And it's sort of a lot of work on CJ's end, my end, to go through, make sure that we're sort of looking through stuff, giving you good feedback. This last set on the factorial designs is going to be had that due last day of finals. But what we also need to do is give CJ enough time to work through the stuff, give me enough time to work through the stuff to get those current sets back to you. So as you go through, and if you made any errors, I want you to make the same errors in this final set that you're going through and doing. Technically, this last set is worth double the points, because sometimes people are right there on the end, and it's kind of a poor position to be in. And if you know you're at a grade level, and it doesn't matter what you get on your last set in order to go through. So technically in the syllabus, the last set is worth double points. So want you all to have enough time to work on it. So CJ and I had talked, would people be comfortable with pushing that deadline back to, like, say, Sunday night or something? Like, honestly, I'm not going to look at your final problem sets on Friday as soon as you turn them in. Know that everybody wants to get on with their lives and sort of put Psych 50, 60 behind them. But it would be helpful, sort of relieve some stress, if we just push the deadline for that back to that Sunday. Okay, I'm getting a couple ahead. Your nonverbal is really hard to read right now. Thumbs up. Yes or no? People fine with that? Okay, cool. You can obviously turn these in early if you want, sort of whatever you need to do with this. But CJ and I will get these turned around as quickly as possible. Get those sent out to you so that you have that stuff to sort of go off of as you're going through and working on this last set. Okay. So we'll do that. Let me know if this works. And yeah, that'll be the game plan moving forward. Okay. All right. Cool. Let's jump in and sort of back into some of these factorial designs. Okay. Going to be working off of that handout that sent you all the 2x2 ANOVA for the expressive behavior. Okay. So we went through, and again, what we were doing here is we've got giving people looking at expressive behavior in a 2x2 design where we've randomized people to watch either a sadness film or an amusement film or a humor film, and then we've either randomized people to express their emotion or inhibit their emotion. So we've got this 2x2 design, okay? And remember that as we went through with this, ran our, did our screening, and then ran through and took a look at our output. What we ended up with is a couple of main effects, and then maybe some weak evidence, or maybe not, questionable evidence for a dependency of the effect of film on expressive behavior relative to instructions, right? So, based on our main effect of film, Riley, what can we interpret this main effect of film as meaning?
That there isn't a main effect?
Okay. Well, take a look at our p-value here. And so for film, yeah, sometimes it's easy to switch around partial A to squared and p-values. So do we have evidence for a main effect of film?
Yeah.
Okay. This is a massive, massive f-test. Okay. This p-value is equal to 1.03 times 10 to the negative seventh or something along those lines, right? So it's incredibly small. And so we have a main effect of film. Now, how many levels do we have to our film condition? Riley?
Oh, sorry. How many levels?
Yeah.
2, right?
2, right? So do we need to do any follow-up tests to determine what that main effect of film means?
No.
No, we don't. If you look at your handout, right, if we go up and take a look at my means here, and this is why I want to be very clear on sort of your tables, your descriptive table, where things are happening here, right? If we have a main effect of film, right? So if I go through and I look at my sadness mean, collapsing across instruction condition is 1.17. My amusement or my humor mean, collapsing across condition is 2.45, right? Rather, one more time, who's showing more expressive behavior across my film condition?
Amusement?
Right. Okay. So remember, this main effect says collapsing across instruction condition, ignoring instruction condition. If we're just comparing everybody who watched the humor film and everybody who watched the sadness film, we're seeing clear evidence of greater levels of expressive behavior in the individuals who were exposed, who watched the amusement film than the people who watched the sadness film. Okay. So ignoring instruction condition completely, if we're just comparing humor versus sadness, seeing more expressive behavior in the humor condition than in the sadness condition. And Erica, does this make sense?
Yeah.
Yeah, right. Probably does. Why is that? Maybe we have different reasons for thinking it makes perfect sense.
Well, I was thinking like social desirability and like what you can express. So you're probably more likely to laugh at something than you are to cry. Yeah.
So that's actually sort of really clutch and turn. I hadn't thought about that. I was just thinking about spontaneous emotion, right? It's easier to make someone laugh than cry, probably. But then there's the sort of social norms and things along those lines, right? And also thinking about the types of stimuli that we're using. Probably easier with watching a film to elicit sort of amusement types of things than sadness things, and some of that amusement to sort of leak through regardless of whatever. And so, this starts to make some sense. Okay. So what I would probably do, if I wanted to interpret this main effect, I would, what I would probably do, just to sort of speed up the process, I would just run an independent sample t-test here. I'd probably just say, okay, now I don't need to because I already know that there's a difference, right? But probably what I would do here is go to my independent sample t-test and just look at expression rating across film condition. Hit OK, right? And so what I could say in this is that sort of have a main effective film, give my F test there, right? And then say that based on my means here, it looks like people in my amusement condition are reporting about a 0.74 unit increase in expressive behavior relative to people in the sadness film. And again, looking at it, we remember in our output, when we ran this, our Levine's test is giving us evidence for a violation of homogeneity of variance, right? And so we've got a reasonably balanced design, but I might be sort of careful about sort of going through and wanting to pull error variances out of my between subjects table or out of my ANOVA table. Probably here what I would do is just default to an independent sample t-test. Just run those, not to get the test because I already know I don't need to run the test. What it's going to do is SPSS is going to give me my point estimate for my difference, and then give me a confidence interval around that, so I don't have to go through and calculate. This confidence interval is going to adjust for violation of homogeneity of variance here, right? And so I would say my main effect here is telling me that I have collapsing, ignoring instruction condition. I have differences in expressive behavior in people who watch the film, watch the sadness film versus the amusement film, right? Based on the data that I've got at my disposal, looks like that difference is we got about close to a 3/4 of a unit increase in expressive behavior in people who watch the amusement versus the sadness, with sort of our data supported estimates for population difference ranging from about a 0.44 to about a 1 point increase. Okay, so just kind of tying all that together here. Okay, so me doing this in SPSS is just a shortcut, so I don't have to hand crank stuff out. What I'm just doing here is looking at the between group difference here. Okay. All right, Allie, what about instruction? What do I got going on here?
Looks like also pretty big main effect of instruction.
Yeah.
Similar to film.
Yeah. Really strangely almost identical in terms of size, right? And Allie, tell me what that instruction condition is telling me.
Based on whether, or was it they were instructed to withhold emotion or express emotion regularly? So there was an effect like based on what they were told to do on their expression.
Okay. And so looking at our means table here, who's generating more global expression? The people who are told to express their allowed to express their emotion, or those who are told to inhibit their emotion?
Express.
Yeah. And where are you seeing those totals in our table here?
In the total section.
Yep, down here. So ignoring film condition, mean global expression for individuals allowed to express their behavior. Ignoring film condition, those told to inhibit. Right, so we've got a difference here. And so if I want to just make an interpretation of my instruction condition, I can say sort of main effective instruction telling me that collapsing across film condition, people who are allowed to express their emotion freely generated greater levels of global expression than individuals who were instructed to restrict their emotion. Okay, Robert, does this make sense?
Yes.
Yeah. Why?
because I was trying to follow, or I tried to go back thing, and then I was trying to go back to the previous answer to see if I missed something, and then I missed the question.
Okay, so why does this make sense? So I've got people who I instructed to inhibit their expression are showing lower levels of global expression than people who I said, yeah, go ahead, just express whatever behavior you want.
Because that was what the instruction condition was told to do.
Yeah. This is just my manipulation. Yeah, this is my manipulation check, right? If I didn't find that people who I had instructed to inhibit their expression didn't show less expression than the people who I said just go ahead and freely emote, right? I'd have some questions about the validity of my manipulation, right? If the people I told to keep it together are expressing the same level of expression as the people who I said sort of do whatever you want, I'd have some problems here, right? So the fact that I do have a clear main effect starts to become important, right? It tells me that my manipulation, at least based on my global expression ratings, look to be acceptable, right? In terms of sort of basically, it's evidence that my design or my paradigm is working the way that it should. Okay. And same thing, probably what I would do, again, because in this design, I got relatively balanced cells, right? But what this is saying is that ignoring film condition, people who are instructed to inhibit are showing less expressive behavior than those who are allowed to freely express emotion. But that in and of itself doesn't give me a lot of important information. I want to look at magnitude, right? So probably what I would do, given that we do have violation of homogeneity of variance, I'd probably just go back into SPSS or whatever program you're using, go to independent sample t-test, and instead of film, look at instruction 0, 1. Okay. And so what I'm saying here is that, oh wow, yeah, how close these two things are is sort of confusing, because again, we were getting about a point, about a 3/4 of a point difference, and again, we've violated homogeneity of variance assumptions, which we knew from our screening. So what this is doing is it's telling me my main difference. Again, ignoring film condition, just looking at express versus inhibit. My people allowed to freely express are showing about a sort of 0.74 unit increase in expressive behavior, with supported values going from about 0.45 to, again, 1. These two effects are freakily close. I'm not sure how that turned out that way, but equal effects going on in this. Okay, and then if I wanted to calculate a means-based comparison, I could go through and do that, right? Sort of calculate my D based on this means and standard deviations with both of these, and then report that. Okay. Questions about sort of how I'm interpreting my main effects here. Okay. Brittany, what about this interaction effect? What can I determine based on this?
That there's not an interaction between film and instruction, right?
Okay. Is that how we interpret null effects?
What did you say? Sorry.
Is that how we interpret null effects, to say that there is no interaction?
There's no evidence for interaction?
Right. And I would say sort of we just have little evidence or weak evidence for an interaction, right? I mean, it's sometimes people would say, oh, this is marginal, right? And maybe move forward. So, or people would say trending, you'll get into trouble with people who are sticklers on this, right? It could be trending towards or trending away. We don't know, right? But regardless of your orientation on this, I can say that we just have pretty weak evidence for a dependency of the effect or differences, fairly weak evidence for evidence that the differences that we're seeing in expressive behavior across our withhold and our express conditions are influenced at all by what film stimuli people are watching. Okay. Ari, what if I, though, was looking at that and I'm like, oh, wow, boy, it's 0.063, right? And 0.063 probably isn't much different than 0.049, right? In a realistic standpoint in terms of strength of evidence necessarily. What if I wanted to say, oh, I'm going to go through and interpret this? Do we have a problem with power in this study?
No, I don't think so. I can't remember what that N was. So.
My mouse just died. Can somebody help us out? What was our N with this? Sample size? Total sample size for this?
I think I found it was a 24. Was that it?
Who said it?
I said it.
Okay, so yeah, just go up to our main table here. How many people do we have in this design?
So we have sorry.
What's our total of our total here in terms of our sample size?
Sorry, 189.
Okay, right. So do we have concerns that our design is overly small?
No.
Probably not, right? Our cell sizes are close to 50, right around there, right? And so it starts to say, now when I asked if we have a power issue, I don't know, that depends, right? I mean, if our effect size is sort of really small, then yeah, we have a power issue because even though we have 200 people, we're not powered to detect sort of really small effects, right? But we start to then wonder if that really small effect sort of makes any difference, if it's practically meaningful for any sort of utilitarian purposes and things like that. So again, sort of thinking about how we want to go through and interpret this. So here, I would say that we have only weak evidence for an interaction effect. Probably, I don't know that I would, if this was just a straight up sort of study, I probably wouldn't maybe press this too much unless I was sort of really looking for this, just because we really have pretty weak evidence for an interaction here. We have a pretty good sample size, so I would probably leave this alone. But again, that's something we could go through and think about. Okay. All right. Questions?
Question. What would this mean if, like, for example, if there was an interaction? I think I understand what it means, but like, since we said there's no evidence or little evidence for an interaction here,
Yeah.
what if there was?
Okay.
What implications does it have?
We'll get into that in just a moment. That's kind of where we're headed.
Okay.
All right. So we're going to go through, take a look. So we went through, ran our analyses. Looks like we have evidence, sort of very, very strong evidence for a main effect of film, right? Which is saying that we're seeing differences in people watching amusement and sadness films. We're seeing differences in expression in people who are randomly assigned to watch the amusement film versus the sadness film, ignoring instruction condition. We're also seeing clear evidence for instruction, saying that ignoring film condition, people randomized to express their behavior showed more global expression than people allowed or instructed to inhibit their expression. And weak or questionable or minimal evidence for a dependency on these two. Okay, so this is SPSS. So we could also go through, if we wanted to go through and calculate. Now, in this situation, for those main effects, probably makes more sense to calculate a D type of metric, just because we only have two levels, right? We can say, so this is the mean difference in standard, or this is the difference in standard deviation units across these two. But what we can do also, remember, we can calculate our partial omega squared. Okay, and we can also calculate our eta squared. Right, we get in our output partial eta squared. Okay, and partial eta squared says once we remove variability that's attributable to other factors, our factor, this is how much of that remaining variability our factor is accounting for. So for my film condition, after I count for variability associated with instruction condition and the interaction, film accounts for about 14% of what's left over in my variability in expressive behavior. Okay, same thing. After I take out variability that's due to film condition and the film by instruction interaction, instruction, sort of express withhold, accounts for about 14% of the total variability that's left over after that, right? And then my film by instruction condition, this is just telling me that once I pull out variability in expressive behavior that's due to main effective film and main effective instruction, I've got about 2% of the remaining variability that I can attribute to that interaction effect. Okay, but what we can also do is calculate a couple other types of effects. Remember that we could calculate our eta squared, and our eta squared is a little bit more intuitive, right? Our eta squared is our sum of squares of our effect over our sum of squares total. And remember, in your SPSS output, we're looking at corrected total here, right? And so if we go through and calculate eta squared for my main effective film, I get about 0.124, saying that film condition accounts for about 12.4% of the total variability in expressive behavior. Instruction accounts for about 12.3% of the total variability in expressive behavior, and the interaction accounts for 1.4% of the total variability in expressive behavior, right? So the difference between partial coefficient and our partial eta squared and our eta squared, partial eta squared, it's the proportion that's accounting for whatever's left over after we pull out our other factors. Eta squared is just all of it. It's our total. Okay. And then we can also calculate our partial omega squared, right? Rachel, what's our concern with partial eta squared here?
For the interaction?
For any of them. What's the concern that we have for eta squared, partial eta squared in terms of effect sizes relative to our omega squared statistics?
It's more positively biased.
Yeah, right. And so what I could do is, and again, eta squared is fine in saying sort of for this data that I'm looking at, what's going on. But in terms of if we're looking for population effects, omega squared and partial omega squared are going to be better statistics because they're going to be they're not as biased as eta squared. They're still positively biased, but they're not as biased, right? So if we see our partial eta squared is 0.142, my partial omega 0.136, 0.141, 0.135, 0.019, 0.013 here, right? So we're seeing some reduction. Now we've got a lot of people in this design, so we're not seeing a huge amount of shrinking. What we would do though is probably just if we wanted to report our omnibus effects as omega statistics, we would probably use these just because these are going to be better population estimates than these here. Questions about, and so up here is just again a reminder on what's going into the calculation of our partial omega squared. Okay. questions about these effect sizes? Okay, cool. So, Allie, Robert, going through and doing this in Stata, you start to get take a little bit different approach to test the homogeneity of variance of your interactive effect, or your 2x2 ANOVA, your factorial ANOVA. What you would do is here, if I generate this is a shortcut for setting up an indicator variable 1, 2, 3, 4 for my film by instruction interaction. Remember in SPSS we went through and we said, okay, express sadness is 1, withhold sadness 2, express sadness or express amusement 3, withhold amusement 4, right? In Stata, we can just shortcut that. We can say egen, I'm going to create a new variable called cell, and that's going to equal sort of group times film by instruction. What it'll do is just give a 1, 2, 3, 4 code there, okay? And then what we can do is we can define, sort of label these, right? So we're saying label define, creating a label, here's our label, and so we're just labeling these 1, 2, 3, 4, what they actually are. And then this is actually where we start to get sort of to the nuts and bolts of things, is we just say, use our var command and our outcome by our cell variable that we just used, and cell is just the cell variable that you're creating is just going to be the same as this condition variable that other people did in SPSS, right? So in Stata, because you have to ask for that homogeneity of variance test separately, you just have to set it up a little bit differently. So you're basically creating sort of each one of those cells is a different group, and then you're just running your rogue var command there. And again, if we take a look at your Levine's test here, 0.029, it's the same thing as what we got up here. So you're just setting it up a little bit differently. Here's your 2x2 ANOVA design. Okay, commands, everything else is looking the same. You can also request your effect sizes once you go through and you run your analyses. If you just type in estat esize, it's going to give you these are going to be partial eta squareds. These are going to map onto exactly what you found in SPSS. Stata is going to give you confidence bounds around that. I think, does Stata do that, right? Or does SPSS do that now? Yeah. Oh, no. Yeah, looks like it's not. So here, with this estat esize command for the two of you, it's going to give you confidence bounds around your eta squared statistic. And then if you follow that up with estat esize omega, this is just going to give you your partial omega squareds. Same thing as before, okay? And if we look at these versus the ones that we calculated here, they're all the same, okay? So just a different way to go about and grab some of those, save you some hand calculations. Okay. This here, so now remember that for everybody, remember when we're doing our one-way ANOVAs and we have a violation of homogeneity of variance, right? So we have unequal cells, violation of homogeneity of variance. Remember that we could request that Welch test, right? Because if we've got different sample sizes or different cell sizes and different violations of homogeneity of variance, what we start to become concerned about is sort of the robustness of our test, right? And so in that situation, we might look to that Welch test to say what's going on and sort of interpret that as our omnibus test. Now, when we get into our factorial designs, there's no alternative to the Welch test. We can see that, yeah, we have a violation of homogeneity of variance, but SPSS is just going to give us our model as if we hadn't violated anything. Ali and Robert, there are ways to go through and model this ANOVA as a regression, right? ANOVA is just a special case of regression. There's nothing unique about ANOVA that you can't run in a regression model. You don't need to worry about this, but this is just a way to go through if we were to find, as we did in this data set, right? For this design, we did find that we had a violation of homogeneity variance. What we can do is we can set this up as a regression model with robust standard errors to give us corrected tests within the context of this. You could set this up in SPSS. Maybe it would be more difficult to go through and do. But just as an alternative, when we start to see some changing in terms of our model effects here to some extent, right? So before, if we run the uncorrected tests, my instruction condition was p less than 0.001. Here, that starts to get smaller. Our interaction 0.063. Here, it's 0.06. So we see some adjustment on this. But again, sort of the thing that we need to be concerned about with these ANOVA designs is violations of homogeneity variance, and then how do we go through and address that is with our follow-up tests. Yeah. All right. I'll go through, send you a write-up of this omnibus test so you kind of see how we're going through and integrating this stuff. I was working on it, but then time ran out, and so I'll send that to you so that you have that kind of as, again, not as a template, but just something to kind of see what's happening with this. Okay. All right. So, interactions. Brittany, and this is what you were asking about. So if we had found an interaction or compelling evidence for an interaction between film and instruction condition, what would we do with that? Okay, this starts to be the crux of our ANOVA designs. Our omnibus tests are fine, but they really don't tell us much of anything that we want to know, right? It just says, hey, the effective film condition on, or the effective instruction condition on expressive behavior changes depending on sort of what film people watched. Like, okay, well, how? What's going on? Okay. First thing we always want to do if we have an interaction or any interaction effect that we were sort of wanting to go through and probe, first thing to always do is plot this out. Okay. Get a visual with our ANOVA designs. Bar graphs are the best way to go about and do this, and go through and see sort of what's happening with this. Okay. So, Erica, with this, and so this is going back to a previous example that we had used where we're looking at the unique and interactive effect of task difficulty and, let's say, cognitive arousal on performance on some task. Okay. Based on this graph here, do we have evidence for an interaction? Yeah. How do we know? How are you able to tell that we have an interaction going on here?
Well, I remember talking about this graph. I don't actually remember why.
If we break it down, and if we just look at the impact of, if we're looking at if we're just looking at easy tasks, what happens as arousal increases for our easy task?
It increases.
Performance increases, right? So as we go to low, medium, and high levels of arousal, if we're talking about easy tasks, performance increases as our arousal increases. What happens if we're looking at difficult tasks, though?
So it's low arousal has low performance, and high arousal has, or difficult. So for low arousal, there's low performance, and for high arousal, there's low performance, but it's higher for medium arousal.
Exactly. We've got a different pattern of effects depending on whether or not we're talking about easy or difficult tasks, right? And again, if I were to say, like, literally draw a dot in the center of each one of these bars, and then connect them with a line, this one's going to go all the way up, right? This one is going to have this V shape here, right? So we've got different lines telling us that there's different things going on at different levels of our study, right? And so what we have here is visual evidence of an interaction, okay? And so what we're seeing with this interaction, it's saying that the effect of factor A on my outcome is dependent on factor B. Or we could flip it around and say the impact of factor B on my outcome is dependent on factor A, right? Erica, if you say, hey, what's the effect of factor A on outcome? In the presence of an interaction, I'm going to say, I don't know. I have to know what levels of factor B are, because otherwise I can't tell you, right? So if you ask me, hey, what's the impact of arousal on task performance? I don't know. We're talking about easy stuff or hard stuff, because it differs. It makes a difference, right? And so visually we can see this, again, if we just draw a line. So we got an increasing function here. Here we've got something that differs up, telling us that we have an interaction, okay? But when we get these interactions, what we need to do is we need to come up with a strategy to determine sort of where this dependency is taking place. What's going on with this, right? And so in terms of options, right? One thing we can do is we can have planned contrast. This is always the high road, okay? These are our theory-based or conceptually based tests that we've planned out before we collect the data, before we look at anything. And we say, I've run these analyses. And the reason I run these analyses is probably not to run the F test. The omnibus test, who cares about the omnibus test, right? I'm not running this project to say, oh, hey, there are differences in there somewhere, right? I should have some idea about what groups are different than what other groups, okay? Other thing with our planned contrast is we're not limited in this, with our planned contrast to just pairwise comparisons, right? Maybe, Erica, one of my a priori contrasts here is based on theory, maybe this turned out exactly like I thought. I was like, well, for difficult tasks, I'm expecting performance in people at medium levels of arousal to outperform the combination of low and high, right? So I could set that up as a contrast and test that where I couldn't go through and do just a pairwise test. I could say is medium higher than low, is medium higher than high, but I can't really sort of tie that all together with this, right? So the contrasts are a nice way to start putting together sort of interesting and important and theoretically meaningful comparisons, right? Other thing I can do is post hoc tests, all right? This is where stuff starts to get tricky with our factorial designs. We need to be careful when we get into the post hoc stuff, because there are comparisons that you could make within this interaction that aren't interpretable and so aren't worth taking a look at, right? The problem is if I just ask SPSS to post hoc the hell out of everything, it's going to correct for all the possible pairwise comparisons, even though all possible pairwise comparisons aren't interpretable, okay? So when we're doing this, we always want to be thinking conceptually about our interpretation, okay? In these interactions, they're mathematically equivalent, right? So I could, with this here, I could think about this interaction and interpret this interaction as the impact of arousal on performance at different levels of task difficulty, okay? So my question could be across what's the effect of arousal on performance at for easy tasks, and what's the difference? What's the effect of arousal on performance for difficult tasks? Okay, I could look at it that way. I could also flip this around and I could say, what's the effect of task difficulty on performance at different levels of arousal? Okay, if I'm asking what the task difficulty on performance is at different levels of arousal, now all of a sudden I'm looking at these comparisons and these comparisons and these comparisons, right? And so here I'm saying what this is 2 units, this looks to be 2 units, but this is now 8 units, right? Either way is a perfectly fine way to go through and think about this. Mathematically, either way is good, but conceptually, one way might make more sense than the other. Okay, so it's important to start thinking about developing an approach to how am I going to break this down? How am I going to go through and start testing some of these things? Okay. Mathematically, they're interchangeable, but conceptually, one way might be sort of more important than sort of another. Okay. So, question. Natalie, what are, based on these two based on these two different ways that we could go through and take a look at things, how many meaningful comparisons could we evaluate here?
For each question or total?
Total. I guess just instead of giving me tell me what would be, if we're just looking at pairwise comparisons, what comparisons might we make out of this interaction that would be meaningful?
I'm not sure I understand your question.
Okay. Just looking at this, Natalie, what comparisons might you be interested to take a look at?
I mean, you could look at like differences between easy and difficult tasks. You could look at.
Perfect. Okay. Looking at easy and difficult tasks at low, right? So again, and this is looking at the impact of task difficulty at different levels of arousal, right? So we could look at low or difficult versus easy versus difficult at low, easy versus difficult at medium, and easy versus difficult as high, right? Those are pretty easy, and those would make some difference. That's a reasonable thing to ask, right? At each level of arousal, what's the effect of task difficulty? Okay. Allie, what else could we go through and take a look at that would be meaningful or potentially interesting within this design?
I mean, you could compare like you could look at differences based on arousal? I mean,
So I could look at differences in arousal at different levels of what?
To difficulty, task difficulty.
Yeah. So what I could do is I could look at, okay, if I'm just looking at easy task, what's the comparison of low versus medium, low versus high, and medium versus high, right? And then I could do the same thing at difficult tasks. I could go low, medium, low, high, medium, high, okay? So what we end up with here is in this example, right? We've got a simple effect of we got what we call this when we get into our interactions, we call these simple main effects, okay? So I've got a simple main effect looking at effect of factor A at each level of factor B, okay? So if factor A is task difficulty, right? I can look at the impact of task difficulty at low levels of arousal, at medium levels of arousal, and high levels of arousal. Okay. I've also got the simple main effect of factor B at each level of factor A. Okay. Here we're looking at the effect of arousal on performance for easy tasks, and then also looking at the effective arousal on performance for difficult tasks. Okay. So overall, here we have 9 simple main effects that we could go through and pull out. Okay. Brittany, looking at this, what effects might not make sense to take a look at?
Well, maybe, I don't know, we haven't talked about performance, so maybe, we have talked about performance. So things that just wouldn't be good to look at.
Yeah, can you see what that might be in this design?
I don't. I'm not sure, honestly.
Okay. So Brittany, would it make sense to compare performance for people completing an easy task at low arousal and people who are completing a difficult task at high arousal?
Well, okay, yeah, that makes sense. It wouldn't make sense to compare the easy groups to the difficult groups at the same.
Yeah.
Is that right?
basically what we've done is in that situation we've crossed factors, right? Performance in people who are completing an easy task at low levels of arousal is a completely different situation than people completing difficult tasks at high arousal, right? And people with looking at performance at a difficult task at low arousal and a medium task and an easy task at medium levels of arousal, that's an apples and oranges comparison. Even if I did find a difference, I don't know how I interpret that because they're different, completely different people, right? There's no shared commonality between that, okay? So if I'm looking at this, I've got 6 different means, right? So I've got 6 means, which means that I have 15 possible pairwise comparisons here, okay? Remember, we take 6 times 6 minus 1, right? So 6 times 5 is 30, divided by 2 is 15. I've got 15 possible comparisons, sort of unique combinations of means that I could look at. But I've only got 9 of them that are meaningful, okay? So Natalie, if I just ask SPSS to run a post hoc on this, how many comparisons is it going to give me?
So you said that there's 9 meaningful ones, and then you're also talking about the
Yeah, so there's 15 total. There's 15 possible comparisons that we could make. There's only 9 that are actually interpretable. But if I just ask SPSS to give me post hoc comparisons, how many comparisons is SPSS going to give me? 15. How many? And with that post hoc, how many tests is it going to control for?
All of them, right?
15. But if 6 of those comparisons aren't anything that I'm actually interested or could ever or would ever interpret, what I've just done is corrected for a bunch of tests that are nonsensical for me to talk about anyway, right? And so what we need to do is have a good game plan before you jump into this to think about what am I going to do, how am I going to approach this, and how am I going to start teasing things apart, okay? And this is the crucial thing. If I'm just running my one-way ANOVA, right, if I've just got one factor, say I've got 5 different levels, okay? 5 different, one-way ANOVA, 5 different levels. Number of possible pairwise comparisons I've got there, 5 times 4 divided by 2. I've got 10 possible pairwise comparisons that I can make. And Rachel, in that one-way ANOVA, are all 10 of those pairwise comparisons meaningful?
No.
In our one-way design.
Oh, yes.
Yeah, right? Because it's just sort of these are the different levels of my thing. I can, technically, it probably doesn't make sense to run all those 10 because probably all those aren't maybe necessarily practically interesting, but I can at least run them. And I could take a look at them and it would make sense. When we get into our factorial designs, we're going to have pairwise comparisons that are going to involve a crossing of factors. And those are nonsensical. We can't attach an interpretation to those anyway, right? And so what we need to do is we need to think about what comparisons can I make, what comparisons are interpretable, and then come up with a strategy that either is only going to look at stuff that's theoretically important, and these are going to be probably our a priori comparisons, or if we do go through and we just really don't know, it's just kind of an exploratory interaction, how are we going to go through and control for type 1 error in a careful way so that we don't just so that we don't undermine the power of our study by just asking SPSS to post hoc stuff or to post hoc stuff for us, and now all of a sudden I'm controlling for, say, an additional 6 comparisons that aren't relevant to anything that I'm doing anyway, right? So we have to have a game plan in terms of how we come up with stuff. Okay? Questions on this? Okay, cool. Let's do this. Let's take 10, come back at 3:25. We'll jump into how we go through and approach this with with our contrasts and a couple different techniques and a couple different approaches we could take with our post hoc stuff. Cool. All right, folks. We'll see you back here in 10.
Can I ask a question real quick?
Yeah, what's up?
I was sitting over here mulling over this interaction stuff. So, these simple main effects that we're talking about, do you decide those before you analyze your stuff?
your simple main effects are your simple main effects. Your design determines what simple main effects are there, right? But what you want to do is think about as the investigator, sort of why did you run this design, right? What specific effects are you interested in looking at, right? So Scott Frank emailed me the other night working on he's trying to run a meta-analysis looking at, oh boy, I can't even remember what type of effects. Basically, looking at whether people are more punitive towards stereotyped groups committing stereotyped crimes, right? Like, so if in this 2x2 design, let's say I have two groups, let's say, and sort of race ethnicity, so let's call it white, black, and two different types of crime, like embezzlement and
assault
or sort of drug charge or something like that, right? And saying that from a second law perspective, that the idea being that juries will be more punitive towards white offenders for white-collared crime than they would for black offenders because there's a mismatch. And the same thing that makes
so much more sense.
Black offenders, sort of juries will be more punitive to black offenders for, say, a drug-related charge because it's stereotypically that, right? And so there you have, a similar 2x2 interaction, right, that's hypothesized. But sort of going in, you have very specific hypotheses about what that interaction should look like, right? And so with something like that, right, you might say, and Hal makes this argument, I don't care about the actual interaction effect, right? I don't, that's not, so what I'm doing this is to look at those simple main effects. So I should expect for white collar crime, I should expect a difference between black and white defendants. And for sort of assault, so I should see a difference between black and white defendants. I'm expecting those to go in a very specific way, right? And so those are the things that I want to go through and take a look at, right? And so having those now, I could look at all sorts of different things, right? But again, does it make sense for me to compare punitiveness for black defendants in white-collar crime and white defendants in drug charges? No, that's apples and oranges. That doesn't make sense, right? So what you want to do is hopefully you're looking for an interaction that you think should go a certain way, and you've got a game plan for how to go through and take a look at that before you move forward. And as our designs start to get more and more complicated, the more factors we add and the more levels we have to those factors, this can get pretty intense. So you just want to have a good game plan before you jump in the middle of stuff.
That makes a lot more sense in that example. Thank you.
Okay, yeah. Other questions about this idea of simple main effects, interactions, and how we might plan to jump in the middle and start teasing some of this stuff out? Oh, okay, cool. So here's our simple main effects with things. All right, so the question now is, how do we go about teasing some of this stuff apart? Okay. Our sort of first option, and probably our most defensible option, is going to be our linear contrast. Linear contrasts are going to be the exact same thing that you've already been working on right now. The stuff that you're doing by hand, we can do that the same thing here, okay? Again, our linear contrast, and probably sort of the formula SPSS uses is a good one to use just because it's simple. You get a standard error estimate. You can go through, calculate your confidence intervals there, sort of good to go, right? This is just going to be the value of your contrast. Same contrast thing that you set up beforehand. Your standard error is just going to be the mean squared error estimate times the sum of your weighted, the sum of your squared weights over cell sizes. This is just the same formula we did with a one-way ANOVA, exactly the same. Okay, so what we would do here, and so to note that this is going to be your mean squared error in this standard error formula. This is going to be taken from a simple effects ANOVA table. Okay, so what this means, and so we've got a handout that we'll hopefully get to looking at a 2x3 ANOVA, okay, where we've got, pull this up. Okay. So in this example that we'll work through, we've got a situation where what I've got is I've got men and women in terms of my participants, and then I have group membership sort of based on endorsement of some beliefs that they have about trauma. Okay, so again, we've got some people who have some interpersonal concerns about the consequences of trauma. People who've been exposed to serious trauma, I would be hesitant to develop relationships with them because, I don't know, I would be hesitant to sort of date someone. I would be hesitant to let someone who's been exposed to serious trauma watch my kids, things along those lines. We have a benevolent group. People who've been exposed to trauma are fine. People exposed to trauma are healthy and as stable as anybody else. And then we have a negative kind of pejorative group. Yeah, people exposed to serious trauma are negative or dangerous. They're unpredictable. They're sort of crazy, like that type of thing, right? So we've got two factors. We've got sex, and then we have class, sort of 1, 2, or 3, okay? And maybe what I do is I find an interaction of sex by class in terms of sort of just overall sort of how much I'm just looking at mood, right? So are there differences? And so if I find this interaction, it says that differences that I'm seeing across my profiles here differ or are dependent on whether or not I'm talking about men or women, okay? Now, in this situation, if I wanted to look at the simple main effect of class across gender, right? So what I want to do is or across sex. So what I want to do is I want to compare interpersonal to benevolent, interpersonal to negative, benevolent to negative for men, and interpersonal benevolent, interpersonal negative, benevolent to negative for women too, right? What I would do is I would go through and probably split my file and run a one-way ANOVA for class separately in men and with women, okay? If I do that, that one-way ANOVA is what I would call a simple effects ANOVA, because I'm just looking at simple effects for men and simple effects for women, okay? Now, generally, when we're talking about our contrasts, this mean squared error, generally most appropriate to take that from that simple effects ANOVA model, okay? For reasons that we'll talk about in a moment, all right? But if I go through and to do that, then running my contrast is just the same as what I've been doing up to this point, okay? SPSS won't allow you to run contrast directly in these factorial designs. You have to set this up on your own. But good news is you all know how to do this. You're all doing it right now. Same procedure. What we're doing is we're just separating our file into sort of looking at differences, my contrast at this level versus this level, and sort of moving forward from there. Okay. Again, SPSS also has their corrected formula, which is fine. I haven't seen anybody argue about that. I can't find sort of strong evidence. There's sort of in the methods literature that sort of good resource for this, but no one complains about it, so we're not going to worry about it right now. Okay, but this is the formula that they go through and use that. Okay. So those are our contrasts. We also thinking about our effect sizes. For our simple main effects and our factorial ANOVAs, still going to use our D-metric statistic, right? And this is just going to be the value of our contrast over some error standard deviation, okay? But again, what we're going to struggle with here is trying to decide what do I use as that standardizer. Okay. So think back to our example that we had where we were looking at task performance as a function of temperature and humidity. Okay. So what we were doing is having people complete tasks people were randomized to 50, 70, or 90 degrees, and people were randomized to humidity, high and low, right? And so looking at the main effective temp, main effective humidity, and the interaction of those conditions, right? If we're talking about a one-way design, okay, remember that in our one-way ANOVA, we're asking, so, okay, is temperature associated with performance? And we ran a one-way ANOVA where we just had people randomized at 50, 70, and 90 degrees and looked at differences in performance across each one of those temperatures, okay? In that one-way ANOVA, our mean squared error, this is our mean squared error contained all the variability in performance that wasn't systematically related to temperature, right? Any variability that was systematically related to temperature, that's going on our mean squared treatment. Everything else gets put over in our mean squared error, okay? So again, for that design, the one-way design where temperatures are our only factor, here's all the variability in performance, right? And what our one-way ANOVA does is it separates that into temperature, variability systematically associated with temperature, and then everything else, right? Because in any of our statistical analyses, if I have variability that's not accounted for by something that I've specifically modeled, it's error, because I don't know what it's attributable to. Doesn't mean random error. It might be attributable to stuff. It probably is attributable to stuff. It's just nothing that I've included in my model, so it's error, okay? But if we switch this over and look at our 2x3 factorial design, okay, where we're modeling both temperature and humidity, now all of a sudden my mean squared error, it now contains variability that's not related to temperature, right, humidity, or temperature by humidity interaction, okay? And so as a consequence here, in the one-way design, I just had error was anything that's not related to temperature, right? When I go through and I take a look now at my factorial design, my error term now is limited to things that just are unrelated to temperature, humidity, and the interaction of temperature and humidity, okay? So, Allie, what does this do to my error term from my one-way relative to my factorial design?
It's probably going to reduce the error.
Yeah. It's going to shrink it up. It's going to be systematically lower, right? And this is great. And this is why we talk about our factorial designs as being generally, everything else held constant, more powerful designs than our one-way designs, because we've got more things that should account for variability in my outcome. And the more variability in my outcome I account for, the smaller my error term is. Riley, where does that error term go in our statistics?
What do you mean in our statistics?
In sort of our F tests and our T tests, where we're sort of in that ratio, where does that error term go?
You mean like the within?
Yeah. In the numerator or the denominator of those ratios?
This is the bottom one.
The bottom one, yeah. The bottom one works. That's perfectly fine. Yeah, the bottom one, the denominator, right? And if I'm dividing things by smaller numbers, Riley, what happens to my output?
If you're dividing by a smaller number, it's a larger output.
Yeah, it gets bigger, right? And so we need to be thinking about this in terms of how we go about with our tests. Is if I'm looking at a main effect of temperature, right? Let's say I go through and I see a main effect of temperature, right? Is it okay for me to use this mean squared error term from my factorial design when that error term has stuff we've extracted stuff related to humidity and the interaction? So what it's going to do is it's going to boost my power, but we start to sort of have questions about whether or not that's a good use of a metric for my effect size. Because what's going to happen is I'm just pulling my mean squared error from my overall ANOVA table. It's going to make this error term smaller. If this error term's smaller, it's going to inflate my effect sizes maybe more than it should. Okay. So when we're thinking about our effect sizes, okay, Howell in this, and Howell's text is fantastic. If you haven't been reading that, make sure that you hold on to that. That's a phenomenal reference for sort of moving forward into your later work. But what Howell's making an argument for is, let's say if this is my if this is my ANOVA table for my factorial design, looking at temperature and humidity, Howell will make an argument that says, well, what you could do if you are looking for calculating an effect size for some contrast that you're running on humidity, okay, or excuse me, temperature. Whatever your value of your contrast is, let's say that we're looking at 70 versus the combination of 50 and 90. Maybe we think 70 is the peak performance. And so for this, what we're doing is we're wanting to look at sort of our effect size for this contrast at low and high levels of humidity, right? Hal makes an argument that what you could do is take the value of your contrast over your error standard deviation, and what Hal's talking about is creating a contrast-specific error term that's going to be your sum of squares error plus your sum of squares humidity plus your sum of squares from your interaction over the top of degrees of freedom error, degrees of freedom humidity, and degrees of freedom of the interaction. Okay, and the idea behind this is that for your effect size, all you're interested in is variability associated with temperature, right? So just going through and taking the mean squared error, the square root of the mean squared error here is kind of cheating, because this mean squared error term has already had extracted stuff related to humidity and the interaction, right? And so the argument is that's going to be too small, and it's going to make your effect size too big, and you're going to think you have a bigger effect than you do. And so what Hal's arguing here is what you can do is systematically, because everything sums to 0 in this table, what we're doing is we're taking variability due to all of our within subjects error, and then we're adding back in stuff that's related to humidity and the temperature by humidity interaction, and creating essentially a sample-specific standardizer for each one of those contrasts. Okay. I present this. We're not going to do this. I think it's a very sort of nuanced way to go about things, but it starts to get into I like it a lot, but given the time we have left in the class, I'm not going to have you fool around with this necessarily. Other sort of options that you can consider, same thing, kind of similar to what we were talking about before with our one-way effect. What you could do in terms of your effect size, you could take the value of your contrast and divide it by the square root of your mean squares from your factorial ANOVA. You could do this, but again, this is probably going to go through and inflate your effect size. It's probably not recommended. Okay. If you've got a situation where you've got a balanced design, so you've got equal people in each cells and no violations of homogeneity or variety, what we can probably do for this contrast is use this square root of the mean squared error from a simple effects ANOVA. Okay. Again, if we think about our simple effects ANOVA, this means this is going to be, like in this one, right? Our simple effects ANOVA, if we found an interaction of sex by class, what we would do is split file by sex and then just run a one-way ANOVA comparing my different classes for men. And then I'd have a different one-way ANOVA looking at different classes for women. This would be my simple effects ANOVA, right? And argument could be that if I have a balanced design, no violations of homogeneity or variance, what we could do is we could take the mean squared error from my simple effects ANOVA, so we're going to have 2 of those, and use that as my standardizer. Okay. Or let's say that I do have unequal cells, violations of homogeneity or variance. What I could do here is then just use the pooled variances of the samples that I'm using. Okay, so let's say, again, going to this, let's say that I do have violations of homogeneity or variance in my simple effects ANOVA, right? And what I'm wanting to do is I want to look at the difference between interpersonal and negative and benevolent and negative. Okay. Here, what I would do is I would just create a pooled standard deviation just that involves the groups that I'm comparing, right? And we've done this before. Not pulling from my overall ANOVA table. I'm just saying, all right, I'm comparing groups 1, 2, and 3, and so those are the variances, the pooled variance that I'm going to construct there, right? Or if I'm just looking at 1 and 2, look at the pooled variance of those and using that as my standardizer. Or standard deviation of control group. Gotta love Glass's delta. Easy, right? You're like, this is my control group. I like this. This is my standardizer. So these are mean differences relative to sort of this group, and sort of moving forward with that. Okay. So again, this is why effect sizes are difficult. This is why they're tricky, and this is why people don't use them probably as much as they should, because it requires quite a bit of thought into how we're going through and constructing these. There's no one right answer. We just have to be thinking about, how do I approach this design? Okay. And so for our contrasts, when we're going through and calculating these, okay, if you've got a balanced design, no clear violations of homogeneity of variance when you're calculating your contrasts, right? These are your statistical tests. You could use your contrast formula and just plug in the sum of squares error from your factorial ANOVA, okay? But if you've got an unbalanced design, possible violations of homogeneity of variance, probably what we ought to be doing is using that mean squared error from our simple effects ANOVA. This is going to be a more powerful test, right? And if you run a beautiful experimental design that's completely balanced, everything's randomized, you can make an argument for capitalizing on this and doing this. But for a lot of applied stuff, particularly for us clinical folks who aren't often running randomized controlled experimental designs, it's like who has pathology, who doesn't, who has some other characteristic, who doesn't. I have nothing that I'm randomizing to. This is probably going to be the more conservative approach. Okay. And then when we're thinking about calculating our effect sizes around these contrasts, if I'm not at all concerned about inflating my effect size, you can use your mean squared error from your factorial ANOVA. But again, this is probably not a good idea. You should be concerned about inflating your effect sizes. It feels good to report a big effect size, but that also contributes to problems in the literature that we're already seeing. Okay, but if we're running contrast on simple effects and you have no clear violations of homogeneity of variance, taking the square root of your mean squared error from your simple effects ANOVA, it's going to be reasonable. Unbalanced design, possible violations of homogeneity of variance, probably your pooled variance of whatever cells that you're comparing. And if you just got a nice baseline condition, Glasses delta is also a nice fallback here too. Okay, so lots and lots and lots of options, lots of things to consider, but probably the very first thing you should be thinking about, and this is why I beat you guys up so much on terms of the screening, is be thinking about, okay, what does my design look like in terms of balance? Do I have wildly unequal cell sizes, or is everything kind of pretty much the same? And then two, what's my variability look like? Do I have violations of homogeneity of variance, or are things looking pretty much A-okay with stuff? Questions on this? All right. Let's do this. So go through, and let's say, and what we're doing here is we're going to go back to our film by instruction example here. Okay. And let's say what I'm doing is I've gone through, and let's say that I have this marginal, or this interaction that I have weak evidence for, but let's say that a priori I believe that I'll see greater reductions in expressive behavior across instruct versus inhibit in my participants watching the funny film versus the non-funny film. Okay, this was a comparison that I wanted to look at before I even ran the data. And so what I make an argument for is, hey, because this was a priori, I'm going to go through and I'm going to test this anyway, because this is something that I want to take a look at. My effect size here, it looks like maybe there's nothing, but don't have strong evidence for an interaction. But I'm still going to go through and want to explore this interaction a little bit more. Okay, so we talked about sort of interpretation here. What I might do is I might go down through, and the very first thing you want to do is go through and plot out this interaction. Okay, and I'm going to encourage you, so we've got, SPSS will give you these marginal means. These are fine just to kind of as a quick look, but when I'm plotting things out, I like using sort of my actual observed means, just because this is actually what's going on in the data. So go ahead and use your actual observed means when you're plotting this out. And if we do that, what we do is we get an interaction effect that looks kind of like this. All right, Erica, I'm going to go back to you because you're my interaction professional right now. Tell me, just based on this graph, is it looking like I have a lot of strong evidence for interaction?
Just looking at the graph, not really.
Okay. Maybe a little bit, right? If I go through and I take a look at, and I draw my line here, right? And I draw my line here, they're not parallel, right? And so, again, this graph, what I'm seeing here, is about consistent with what I would probably expect from an interaction effect that's 0.06, right? It's not there, but it doesn't look super compelling, maybe. But what I want to know is, so I want to go through and run my follow-up tests. Okay, so Riley, what are the follow-up tests that I could run? What are the comparisons that would be reasonable in this interaction?
Like, oh my gosh, it's so quiet. Maybe, I mean, wouldn't you want to compare like the sadness and amusement across both of them?
Okay, yeah. So be a little bit more specific. Sadness and amusement across both of what?
Like across express and then across withhold.
Okay, so I could do that. I could look at, so just, if you're saying I want to look at sadness and amusement across express and withhold, I could compare sadness and amusement for my express condition, and I could look at sadness and amusement for my withhold condition, right? And those would be reasonable to take a look at, right? But if I'm thinking that I'm going to find, if my a priori hypothesis is that I'm going to find a stronger effect of inhibition or a stronger effect of instruction condition in my people watching my funny film versus my sad film, what comparison should I be making there?
Then you'd be like doing the opposite, like comparing the like sadness people across expressing and withholding.
Yep. Perfect. Okay. So really, based on my question, what I'm actually interested in, probably what I'm going to do is I'm going to compare express and withhold for people in my sadness group and express versus withhold in people in my amusement group, right? The first set of effects that you talked about are completely legitimate. Like, I could look at those, right? My question is Am I interested in on whether or not people express more in response to sad films versus funny films? That might not be sort of exactly what I'm sort of interested in. What I'm interested in is I'm saying this effective inhibition is going to be more pronounced in people watching amusement films versus people watching sadness films. And so what I might do then is say, in my game plan, in terms of how I'm going to go through and do this, I'm going to say, okay, Natalie, how many comparisons do I want to make to answer my question that I have?
Two?
Yeah, perfect. 2, right? And this is the thing with our a priori contrasts. There are 4 possible comparisons that I could make in here that would make sense in terms of pairwise stuff. I could look at, for my express, I could look at sadness versus amusement, and for my withhold, sadness versus amusement. In my sadness condition, I can look express withhold. In my amusement, I can look express withhold. So there's 4 possibles that I could look in here. But really, to answer my question, I only need 2, right? I could run 4, but then I have to explain a bunch of stuff that I don't really care about, right? And so what I'm going to say is my a priori hypothesis is I'm going to compare express withhold my sadness group and express withhold my amusement group and see if I'm having any sort of signal of greater effects in this film condition as opposed to this film condition, okay? Now, Rachel, how many possible comparisons could I make out of these 4 means?
4?
4 that are meaningful. How many possible combinations could I have with 4 means?
8? I don't know.
Okay. Shortcut here is just the number of means that you have times the number of means minus 1 divided by 2. So we've got 4 means. 4 times 3 divided by 2 is 6, right? So I could look at sad express and amusement withhold and sadness express, or sadness withhold and amusement express. So there are two comparisons in this set that you could run comparisons against, right? Like the statistics police isn't going to show up and kick down your door. But what you've essentially done is run comparisons that are uninterpretable, that don't mean anything, right? And so again, this is with these designs where it starts to become important to have a game plan and say, what are my questions? What do I want to know? What's important to my research? And then developing a plan to go through and test those, okay? But as Riley noted, what we want to do here, based on my question, is we're going to look at sadness, we're going to look at express versus withhold for my sadness condition, express versus withhold with my amusement condition, and see if we're having evidence of different effects. Okay. So what I can do is I can go through and I can split my file by film, right? Because I'm wanting to look at express versus withhold separately within each one of these, right? So in SPSS or in Stata, right? This would be a by sort, right? What I can do is I can go through and I can sort or split my file by my film condition and then just run a t-test here comparing express withhold in my sadness group and express withhold within my amusement group, okay? And if I do this, right, this is just what I get, right? This is just a t-test. T-test, you guys love t-tests. You've been doing t-tests for so long. All we're getting here is just a t-test, okay? So Ari, if I go down through and I take a look at this independent sample t-test, what is this telling me here?
There wasn't meaningful
Okay. No. Okay. So quick. So make sure we're looking at the right columns here. So do I have evidence for a difference in global expression for express versus withhold in people exposed to the sadness film? No, you're on mute.
Sorry, what was the question one more time?
Okay, so we've got a comparison of express versus withhold, specifically in people watching the SAD film. Do we have evidence for differences in global expression here?
Oh, yeah. Sorry.
Okay, cool. And which are you reading are you looking at the top row or the bottom row here? Equal variance is assumed or not assumed?
At the top row?
Okay. So we've looked at our Levine's test for this. So just looking at, and all we're doing is we're taking anybody who watched the humor film, pushing them aside. Just looking at folks who watched the sadness film. Looking at Levine's test, is that telling us that we have evidence of differences in variability across my expression withhold condition? Based on Levine? Again, you're on mute. Oh, there you go. Okay. Yeah. Remember here, what we don't want to see is we don't want to see a small p-value for our test, right? Anytime we're running a test, hypothesis test, it says these two things are the same, right? My small p-value says that it looks like these two things aren't the same. The assumption with my homogeneity variance is that the variability looks to be relatively equivalent. Here I've got a violation, so what I'm probably going to do down here is go down and look at equal variances not assumed and take a look at this bottom line right here, okay? So if I do that, I see that I do have a difference. And if I look at my mean, I'm saying, as I might expect, I'm seeing more expressive behavior in those individuals who are permitted to express their behavior versus those instructed to withhold. So I've got my test, I've got my t-statistic, I've got my test, I've got my mean difference, right? The difference between these is about 0.5 point. And then down here, I've got my confidence bounds for that, okay? If I go through and I scroll down, same thing. I'm getting now a test of express versus withhold specifically for my amusement condition. Okay, and if I'm looking at this, what I'm seeing is that Natalie, you want to help me out with this one? What am I seeing in this one here?
You're seeing that expression rating. I'm having trouble wording it, but they're like the p-value is 0.000, so it's pretty small.
Okay. Do I have evidence for a violation of homogeneity of variance here?
Yes.
Okay, look at my Levine's test. So what's my p-value for my Levine?
Oh, no.
Okay.
Because the value is 0.214.
Yeah. So again, remember it's sort of at the start of this, we went through and our Levine's test for overall 2x2 told us we had potential violation of homogeneity of variance, right? But as we go down through and we're taking a look at these simple tests, right, what we're seeing is 4 people in the sadness film. Looking like we're seeing differences in the variability of expressive behavior. Here we're not doing it. And so, Natalie, which row are we going to interpret for this simple effect?
The bottom? Wait.
Okay. Equal variance is assumed or not assumed? The top one. Yeah. Okay. So here I have a Levine's test with a large p-value. Tells me that probably don't have much evidence or much reason to worry about violations of homogeneity of variance. So I'm going to go ahead and I'm good to just go ahead and interpret my uncorrected tests. Here we've got a mean difference of about 1, lower and upper limits, right? Here though, for our sadness film, we do have some actually pretty strong evidence of a potential violation of homogeneity of variance. So we drop down to equal variance is not assumed. Again, mean difference, that doesn't change, but my confidence bounds will a little bit. Okay. People see what we did here. So essentially we went through split file by film. So we're just looking at these, and it just pops it out easy for us. Okay. If I go through, and what I might want to do here is calculate an effect size, and then my contrast. Did I do that? Okay, yeah, I did it, right? So here, this is just the value of my contrast, my comparison, and the confidence bounds. Oops. And this, I'm just pulling from my tables here. Okay. I also went through and calculated my confidence interval and stuff with my handy dandy calculator here, right? And reported that here. And so we get into an interesting thing, because my hypothesis was that I would see a stronger impact, sort of more differences in individuals with a stronger effect of expression in people who are exposed to the amusement film versus the sadness film. Now, my overall interaction tells me I don't have a lot of evidence for that as something that's reliable, interpretable, right? But I went through and followed up anyway. And this is what will happen sometimes, even when you get interaction terms that are sort of we clearly have evidence for. If I'm just looking at my p-values, and if I'm taking kind of just a standard traditional approach, I say, well, I have evidence of a significant effect of express versus withhold for sad films, and I have a significant effect of express versus withhold for amusement films. So it looks like the same thing's going on with sadness and amusement. So I don't know how to interpret this, right? That could get confusing. But if we're looking at our effect sizes and our our point estimates of the differences that we're seeing, what are we gleaning from this, Allie?
There's a much larger effect for the humor film than the sadness film.
Yeah. The observed difference that I'm seeing across in expressive behavior in my humor for people watching my humor film is about twice what it is for the sadness film, right? Same thing for my point estimate, my effect size, considerably larger for the humor film and my sadness film. Now, if my question is there a difference between humor and sadness? Yeah, like clear evidence of a difference, right? That's sort of not really interesting. But if I'm actually looking at the magnitude of that effect, magnitude of the effect looks like it's noticeably larger for people who I asked to watch a funny film versus people who were just watching this sad film. Now, there's considerable overlap in these confidence bounds, right? And once again, if I go up and I take a look at my interaction, I don't have strong evidence for a dependency of instruction condition on the type of film that I have, right? But if I was really sort of wanted to take a look at this and sort of see, well, sort of what's going on here, what's the nature of this interaction, it's at least going sort of, it's looking like it's going in a direction that's consistent with what I would expect, which maybe is something that I might want to think about if I'm sort of wanting to use this paradigm for my own purposes. And I'm really wanting to sort of tease out, sort of getting a big effect for impact. Maybe I'm wanting to select to use a funny film as opposed to a sad film, just because I'm looking like I'm going to get a bigger discrepancy with that. Okay. So do people see how we kind of jumped in and teased out some of those interactions? And again, main issue here is that based on our omnibus test, we don't have strong evidence that the effective express or inhibition or the effective instruction condition is dependent on film, right? It looks like maybe there's not anything going on there, but it's not something we have strong evidence that we could say definitively, yeah, I think this is going to pop up. But again, a demonstration on how we might go through and start teasing this stuff apart.
I have a question.
Yeah.
On the effect size thing that you just showed us on the follow-up test, the G is the effect size, right?
Yep.
Okay. That's psi. What is that looking at?
That's just
psi?
Yep. That's just the value of our contrast. Okay.
Okay.
And so here,
is that like your? Sorry, go ahead.
Yeah, and here it's just a pairwise comparison that we just ran with t-tests, right? Mm-hmm. But if we were in a situation where you had 3 or more levels to whatever my factor was, then we could start playing around with actual contrasts using the stuff that we've got here.
Okay. So the linear contrast stuff is telling you basically like your confidence bounds around your contrast?
Yep.
Okay.
Because again, and this was a question that came up. People sort of sometimes, so always make sure that you know what you're calculating confidence bounds around, right? Here, it's a point estimate of the difference between my two groups, right? And contrast is, and so contrasts, when we think about contrast, we're typically thinking about situations where we've got 3 or more groups, but we don't have to, right? Any comparison is a contrast. Contrast is just a difference, right? So t-tests are contrasts, technically, right? Here, we just went ahead and took a conservative approach and just ran them with independent sample t-tests within each level of our group, and that's going to be a fine way to approach things. You lose a little bit of power, but no one's going to be able to argue with you against you taking that approach, okay? We can get more elaborate, and we can start to pull error terms from our overall ANOVA. And sometimes we'll need to do that if we want to run actual sort of contrast where I'm looking at 1 and 2 versus 3 or 2 and 4 versus 1, like that type of thing. But if you're just looking at 2 groups, you'll lose power sometimes. But sometimes just falling back on t-tests is the best way to go through and do things. Other questions? Okay, cool. Let's do this. Let's go through, take the final 10 of the semester, come back at 4:20, and what we will do then is we'll go through, talk quickly about sort of approaches to post hoc procedures, and then finish up with a demonstration on some stuff. Okay. All right, we'll see you in 10. All right. Questions before we jump into this last portion of things? All right. We'll go through and pull you guys back in here. All right. So talked a little bit about going through and running some contrasts on things, and we'll finish with a quick demonstration on this. But the other thing we want to think about are some post hoc tests, okay? So the thing that starts to get tricky is in terms of thinking with our interaction effects, how many pairwise comparisons are there that we can go through and take a look, right? So if I've got a 2x2 interaction, right, there are 4 comparisons that I could make, right? And we went through with this last example, sort of 2x2, talked about those, right? But as my design starts to get bigger, the number of pairwise comparisons that I could make starts to get higher, right? So on a 2x3, I've got 9 comparisons that I can make, right? I've got, if I'm just looking at A1, I've got here, here, here. So I've got 3, 1, 2, 3, 4, 5, 6. Then I got 7, 8, 9, right? So I've got 9 in that 2x3 interaction, right? A 3x3, I've got 18, right? I've got 3, 6, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? If I get into 3x4, now I've got 30 pairwise comparisons. If I start adding factors, a 2x2x2, right, and I get that 3-way interaction, I've got 12 comparisons that I can make, right? So we've got 1, 2, 3, 4. We've got 5, 6, 7, 8. Then we've got 9, 10, 11, 12 there, right? A 2x3x3, now I've got 24 pairwise tests. So this is just saying that as we need to be careful about our designs, right? As we start adding on factors and adding on levels, these things will blow up very, very quickly, okay? And so one of the things that we can do, and we don't want to do, is just request an SPSS, request post hoc tests. What SPSS is going to do is it's going to correct for all possible comparisons. With these interaction terms, not all possible comparisons are interpretable. So what I'm going to do is I'm going to end up correcting for 30 tests when all I can really look at are, say, 16, and that's going to impact my power. Things that I probably should be able to claim evidence for are going to fall below because I've corrected for way too many stuff. And so we have problems with reduced power in our test. So wanting to be careful and plan out how you're going to approach this. Okay. So one thing that we can do is we could take a modified 2-key approach. Okay. And this is just sort of using what you know about 2-key to work through the nuts and bolts of stuff. Okay. So here what you would do is maybe look at, and so again, this is a post hoc, right? So you're wanting to look for all possible pairwise comparisons. So let's say you've got a 2x3 design, right? And so you say, okay, there's 9 interpretable pairwise comparisons I could make out of that interaction. Okay. So what you would do, determine how many meaningful comparisons that you want to make. And then let's say that you go through on your 2-key table and try and find an R value that is going to be at least reasonable for the number of comparisons that you're targeting, right? So if I look on my 2-key table and I set R equal to 4, that's going to control for 6 comparisons. I wanted to control for 9. If I go R of 5, that corrects for 10 comparisons. It's a little more, but it's post hoc, so maybe I'm fine being a little bit more conservative, okay? I can also sort of, and again, this is sort of like freestyling stuff, right? You can also adjust your alpha level, right? There's separate tables for alpha 0.05, alpha 0.01. So, probably if I want 9 comparisons in a 2x3, I might just pick R equal 5 and decide that my post hoc tests are going to be a little bit more conservative. Or maybe, I don't know, you say I'm going to set R equal to 4 and just set my alpha to 0.01 and just try that. That's probably, 5 is probably the better way to go on this. Okay, but anyway, you go through, identify your R that's going to match up close enough to the number of comparisons you want. Then you can go through and based on that R you're using and the degrees of freedom, you calculate a Q critical value, and then translate that Q critical back into a T, and then go through and just run your t-tests with whatever your modified critical value is. Okay, and then what you can say is you can say, okay, well, this t-test exceeded what my critical value was based on my back translation of Q. And if that's the case, then I can say, okay, then that's sort of something that's reasonable, or sort of that's not, sort of moving forward with that. Okay, so again, this is just going through and kind of trying to use Q2 to adapt to sort of the comparisons that you're making. Howell talks about this as something that you can do. So this is sort of an option. Okay, the thing that I've come to like more, though, because it's just a little bit better, is or is just a little bit easier to apply, a little bit more precise, something known as a Benjamini-Hochberg procedure. Okay, what Benjamini-Hochberg is doing is it's focused on false discovery rate as opposed to family-wise error. Okay, family-wise error, we're concerned with the probability. What's the probability of committing one or more type 1 errors in this set of comparisons? Okay, what I'm assuming with this is that my whole set of conclusions are faulty, even if I make one type 1 error, right? Benjamini-Hochberg is going to ask, of my total significant effects, right, of the effects that I identify as interpretable, what percentage of those are false positives, right? How many of these are sort of, oh, whoops, I said there was something when I didn't expect there to be, right? And so what the procedure is doing here is it's going through and it's trying to control for that false positive rate. So setting this up is actually pretty simple. Spreadsheets are nice for this. What you want to do is you want to determine a critical p-value for a series of successive contrasts. Okay, so let's say that I have 9 comparisons that I want to make. What we'll do is you set up a p-value for each a p-value, or basically an alpha level for each one of those contrasts based on where they are, the position they are in your set. So my p critical is going to be I, which is your test index, divided by k, the total number of texts, multiplied by your alpha level. Okay, and so what you'll get is, what I would do is I would go through and set up, let's say I've got 9 different tests. Okay, what I would do is I would enter those tests. I would run I would run my tests, and then I would put those in my spreadsheet and order them in increasing absolute size. So here, my contrast 0.345, that's my lowest, and then my next largest, and then my next largest, and then my next largest, so on and so forth. Okay, and what I'm going to do here is I'm going to record my p-value for that t-test. Okay, and then what I'm going to do is I'm going to order these up in sort of my index. So my very smallest test, my smallest test value is going to be 9, and then we're going to 8, 7, 6, 5, 4, 3, 2, 1, right? So put this down. And then what I'm going to do is I'm going to create my Benjamini-Hochberg, my p critical. Okay, and what this is going to be calculated as my index number, okay, for my first one is 9, over the number of tests that I'm running is 9, times my alpha level is going to give me p equal 0.05. Okay, but for my 8th one, so my next highest one, I'm going to say my I is 8, divided by still 9, times alpha 0.05, and my p starts to get sort of smaller. And then as I go down and continue this, my p-value is getting smaller and smaller and smaller and smaller, and what I end up with is an adaptive test that goes through and controls for my false discovery rate, where I've got a different criteria for each one of my tests. So as my test gets farther and farther, larger and larger and larger, my benchmark gets more and more stringent. For things that are lower, less stringent. And so what we can do, as opposed to our modified Tukey, where we're kind of saying, well, I need 9, I can control for 10, sort of playing around with that. Here, you just say, I've got 9 tests that I need to correct for. I'm going to manage my false discovery rate for all 9, and then I'm just going to list this out like this. Okay. And so what we can do, I didn't send you this test, but I will. is I can end up with something like this. Okay, so here in this example, we're looking at levels of conservatism across sex and religious identification. Okay, again, this is a hypothetical example. I can't even remember where I got these data from. It's sort of a made-up example, but sort of here we are. So what we're looking at is, is there an interaction? Does differences in conservatism, self-reported conservatism across individuals from different religious identities, does that differ across men and women, right? And if we go down through and take a look, we do get an interaction of gender by religion or sex by religion here. And so then what we go down through is we map this out, kind of take a look. But this is a 2x4 design. And so we've got a whole lot of possible comparisons in here, right? And if this is completely exploratory, that's a lot for me to manage, right? So what I do is I can go down through and run some stuff, and eventually I get a Benjamini-Hochberg table here where I've got 16 pairwise comparisons. What I've done is I've run all these as t-tests. I've gone through and ordered up all my t-tests in increasing order of magnitude, okay? I'm putting together my p-values. Then I've got my Benjamini-Hochberg p-value, right? And so none of these are meeting benchmarks for interpretation, right? Until I get to these last two, okay? And for these last two, my p-value of my test falls below my p-value, my Benjamini-Hochberg p-value. And so the same thing here. And so what I've got is I've got my first and my second contrast. So what we're seeing is differences in women with no religious affiliation versus Protestant, and women with no religious affiliation versus Catholic in terms of overall levels of conservatism. Here's my difference, right? So here for my index 2, I'm getting about 3/4 of a point difference. Here we're getting close to a point difference. Here's my confidence interval. Here's my effect size, confidence interval around that. This is just a nice way to go through and order this stuff up. Okay, and then what I would do is I would go through and make an interpretation on sort of what I've got going on here. Okay, we're not going to get to sort of working through this, but I've got a demonstration video that I'll give you a link to that walks through this. So you can go through as you're getting into this set. You can go through and kind of see how we're going through and putting this stuff together. Oh, whoops. That's not what I wanted to do. All right. I'm not sure why I thought Joe, like that was a joke at one point, but I forgot what the joke was. And so now I just have a residual Joe Dirt picture in there, which now is funny for different reasons than probably was when I originally put it in there. So it's something that, at least for me, keeps on giving. Higher order designs, this is just looking at sort of interactions with sort of 3-way interactions, 4-way interactions. I mean, this starts to get super complicated. Don't venture into that unless you have a really good reason to do so. But we can kind of go through and take things from there. Okay, I'm not going to ask you to go through and do that stuff, but questions about sort of any of our approaches at this point? Okay, so let's do this. Let's go through. Oops, don't need that. And if you would open up this, you all just open up that 2x3 handout that I sent you. Okay. And what we're going to do is we're going to go through and talk about how we would go through and maybe run some contrasts with some actual real data using some simple effects ANOVA types of things here. Okay. So the data set that I'm using, oh, whoops, that's not the right one. Okay, so what I've got, I'm going to move you guys out here so give me a little more space. What we've got is a group of people, people who we've classified into different categories based on their beliefs about trauma and its potential consequences. Okay, and we've gone through, given them a questionnaire, and then categorized them into different groups. We've got, as we talked about, our interpersonal concerns group, our benevolent group, and our negative group. Our negative group, these are people who say pejorative things about people who've been exposed to trauma. They're dangerous, they're harmful, they're crazy, things along those lines. We've got people who are generally benevolent. So these are people saying, yeah, they're sort of just the same as everybody else. They can lead happy, productive lives. And then we've got some people in the middle say, yeah, no, they're happy, productive, but I sort of might be hesitant to have a relationship with sort of one of these people, right? So we've got people grouped into these three groups. We're also coded whether or not people are identifying as men or women. And then what we've got are overall mood ratings, positive affect and negative affect. And what we might want to be concerned about with this from a manipulation check standpoint is, so I think what I've got here in terms of my classes are that sort of different people from these different profiles truly have different beliefs about trauma and its consequences. But maybe it's just people in the negative group are just habitually negative people, right? Maybe they're just people who are in a bad mood, so they said negative stuff about trauma survivors. Maybe the people who are benevolent say are in a good mood, and so they didn't, right? And so what we want to do is we're going to go through and we're going to run a 2x3 ANOVA looking at the unique and interactive effects of sex, class on negative affect here, okay? So this is a set that I've gone through and already screened. And so what I'm going to do is I'm going to go down to Analyze, Generalized Linear Model, Univariate. I'm going to look at sex and class as my fixed factor, negative affect as my dependent variable, and then I'm going to ask for, we can ask for marginal means, that's fine. Options, we'll ask for descriptive statistics, effect size, homogeneity test. Call that good. Okay. I'm going to hit OK. And so if I do this, what I'm seeing here, make sure that my results are lining up with okay. So we're going to skip positive affect and go right down to negative affect on this. Okay. Well, I guess just for the purposes of this, so if we run this on positive affect and negative affect, Robert, are we seeing any effect of sex by class on ratings of positive affect in this model here? No, we got a big goose egg, right? So maybe disappointing for me if I was really invested, thought there was going to be differences in positive affect, but if not, sort of sweet, that makes it easy to address. We have no evidence of anything going on here, right? But if we go down through and we take a look at negative affect, right? Now all of a sudden we're seeing maybe something different. Robert, what are we seeing? I guess we'll just work off the handout here. What are we seeing in terms of effects for negative affect?
We're seeing that based on the mean, there's evidence of violation of homogeneity of variance.
Okay, so yeah, we've got across our cells, it looks like the variability of negative affect is not the same, right? So we're getting differences there, okay? What else are we seeing in terms, so that's good. And if we go up and we take a look at our cell sizes, Robert, do we have a balanced design here?
No.
No, not even close. Not even close, right? So we've got a hugely unbalanced design and a violation of homogeneity of variance here. So these are things that we're going to be thinking about in the back of our mind, okay? So now if I go through, you're on a roll. If I take a look at my ANOVA table, what am I seeing evidence for based on my tests here?
We're seeing a main effect of gender on difference.
Yep.
Is that what you're looking for?
Yeah. Okay. So we got a main effect. We may got a main effect of sex and a main effect of what?
And class.
And class. Okay. Do we have evidence for an interaction?
No.
No. Pretty cleanly not, right? So what this is saying is that I'm seeing differences in negative affect across men and women, and I'm seeing somewhere across my negative, benevolent, and interpersonal groups some differences in negative affect there. Okay. Erica, do I need to run further up follow-up tests for my effective sex here?
No, because there's only two.
Yeah. If I go back up and I look at my total for men and total for women, looks like I have, and again, sort of these are very large samples, right? So I've got 228 women, 105 men. It looks like slightly higher levels of self-reported negative affect on the PANIS for women versus men, right? So what I can do is I can go through and run some sort of in SPSS, just shortcut it, just run a t-test, see sort of what that point estimate is, effect sizes and stuff like that, just looking at women here, right? To get some of the things that we had looked at again previous, right? But I'm also seeing this main effect of class, okay? So my question is, how do I want to go through and test this? Well, maybe before I even ran this, I had expected a main effect of class, and what I had said is that, you know what, I'm betting that my negative group, my negative class, is going to have higher levels of negative affect as compared to my interpersonal and benevolent. Okay, and if that's what I'm predicting, Allie, what am I talking about here?
Sorry, wait, can you say that again?
So a priori, I'm saying that my negative class is going to demonstrate higher levels of negative affect than the combination of my interpersonal and my benevolent class. What am I talking about here?
Just a contrast.
A contrast. Okay. So my question is, how do I go through and how do I calculate that contrast? Well, if we go to our contrast, right? My contrast formula is just value of my contrast over standard error estimate. Standard error estimate pulls my mean squared error out of the mix, right? But am I confident in using my mean squared error as a good overall measure of error variability for this design? Probably not, right? I've got wildly unequal sample sizes, right? My cells range from 34 at the smallest to 110 at the largest, right? So I've got wildly different cells, right? cell sizes. And I've also got very clear evidence for what appears to be pretty clear evidence for a violation of homogeneity of variance. And so what I might do is I might say, boy, you know what? I'm not comfortable just pulling that mean squared error and calculating by hand a contrast of this contrast using mean squared error for my overall ANOVA, because I've got too many violations here. Okay, so what I could do instead, this is what we're doing in handout. What I can do is I can go to Analyze, go to Compare Means, and I can go to One-Way ANOVA. Oops, missed it. Okay. Because, Riley, based on this interaction, do differences in class, are my differences in negative affect I'm seeing across class, are those dependent in any way on sex?
I don't think so.
Yeah, why not? If they were dependent, what would we see?
We'd see. I was about to say a dependence, but that's not the right answer.
If the effective class was dependent on gender, what would pop up in this in this effects table?
An interaction?
Yeah, my interaction, right? And clearly, there's very little to no evidence that the impact of class is systematically associated with gender. And so what I'm going to do in SPSS is I'm going to go to my one-way. I'm going to look at positive or negative affect by class, and then I am going to go to my contrasts, right? And for my output here, my groups are ordered interpersonal, benevolent, negative. Okay. So what I'm going to do in SPSS, I'm going to set up my contrasts as negative 0.5, negative 0.5, and 1. Okay. Rachel, why does that contrast make sense given my hypothesis?
Because it lines up with the direction that you'd expect the effects to be in.
Yep, lines up with the direction. I'm comparing the combination of two groups relative to my negative group. My negative group is last. Just take the inverse, right? So I've got 1/2. My weights here are going to be 1/2, and -1, right? And so that lines up to help me compare my interpersonal and my benevolent group against my negative group. I'm going to go through, do this, hit estimates for effect here, and hit continue. Options. We'll ask for descriptives, homogeneity of variance, my Welch test. And then I'm going to hit OK. All right. So what we're going to see is we go through, and here's my means table, which is a nice thing to have. Here's my homogeneity variance test, but I already knew we had violations of homogeneity vary for my overall, right? So I can ignore this. Here's my overall ANOVA. I can ignore this too because I already tested this in my 2x3, right? What I'm really interested in here is my contrasts. Now I could have done this by hand, but I'm going to ask SPSS to do it because there's no reason to do things by hand if SPSS will do it outside of if I told you to do it. But what we're seeing here is we've got interpersonal and benevolent versus negative, right? Here we can just pop this up. And what we've got here then is my contrast coefficients, and which one of these tests am I going to use Allie, the equal variance is assumed or does not assume equal variances?
Does not.
Yep. Because this is the whole reason we're using our simple effects ANOVA to run this interaction anyways, because we've got unequal samples, we've got violations of homogeneity variance. And so I go through, and Allie, what is this telling me?
That there's some evidence against the null. So, yeah.
Yeah. So here, value my contrast. Looks like I've got about a 2-point difference on the PANIS, with people in my negative class showing about 2 points higher in terms of negative affect relative to people in the combination of my interpersonal and benevolent class. Okay. And this was older version of SPSS. Let's see what, all right. So here we've got, okay. So if we go down through and take a look at what appears to be going on in SPSS, looks like Cohen's D is using pooled standard deviation for these groups. Hedges G, this is looks like it's giving Hedges unbiased G, same thing that like Stata does with this. And so we're giving, here's a standardizer, here's point estimates of X and things along these lines. Okay. So this is an example. Now, this doesn't get into interactions, but what we've got here is a scenario where we've got an a priori hypotheses, right, that we want to go through and take a look at. And so we want to run a contrast, but given our design, we've got an unbalanced design, and we've got violations of homogeneity of variance. And so I'm not comfortable just pulling my mean squared error from my factorial table and using that to calculate my contrast, because I don't know that that's a good metric of anything, right? So what I'm doing is I'm going through and I'm running a simple sort of just a straight up ANOVA model, because I know that the effect of class has nothing to do with that interaction, right? So I'm just looking at class, running in SPSS my contrast there, and then making my interpretations in addition to effect sizes and confidence bounds and things like that, which are all given to me here for my contrast. Okay. Now, if this was a different situation, okay, and I had a nice, let's say Ari's run, oh, there you are. I was like, where did Ari go? Ari's run in Meredith's lab, a nice controlled design where people are randomized to different groups. Everything's balanced. There's no violations of homogeneity of variance. Then, in that situation, Ari, maybe you want to go through and use the mean squared error out of that factorial ANOVA and just run your contrasts there. That would be a perfectly acceptable thing to do. But oftentimes, more often than not, I've got unbalanced designs. I got violations of homogeneity of variance. Take a little bit of a hit on power in terms of things. But what we go through and do is falling back to just this ANOVA design, so looking at the main effects there, or simple main effects. If, let's say we did have an interaction of sex by class, and I wanted to look at differences, run these same contrasts separately in men versus women, what I could do is split the file by men and women, run this one-way ANOVA in both groups, and just run the same contrast in both of those groups, and then just interpret that. Okay. So all of these procedures are outlined and laid out in the handout I sent you. Okay. So that should give you a good guide. And Allie and Robert, I'll get one of these put together for Stata as well, so you sort of have something to work off of. I have what's for me a relatively short video, is just 35 minutes of sort of me on a demonstration of me walking through that Benjamini-Hochberg technique for a different set of data. I'll send you that handout and sort of a link to that video so you can kind of see sort of a work through on that, sort of work through that on your own. But again, let me know if you have questions. But this should give you a good sense for how to break these up, how to go through and work on some of these designs. And so we'll leave it at that. Moving into this last set. Okay. Questions. How are people feeling in terms of these factorial designs? There's a lot going on, a lot of things to consider. So as you're going through, again, sort of number one thing I can recommend is having a game plan. Sort of saying, okay, sort of these are the things I need to take into account. And generally it's balanced design and violations of homogeneity of variance, right? So what's going on there? And then setting up an approach, okay, given these things, how am I going to run my follow-up tests? What should I be thinking about using in terms of a standardizer, in terms of my effect sizes, so on and so forth. Okay. All right. Any questions?
I wanted to ask, how does the last problem set being worked double help us? I've been trying to think of it, and I don't know why.
Yeah. If, let's say I'm sort of on the cusp of that A-B cusp, and what ends up happening is, even if I got a perfect score on that last assignment, I would still be like a 1/10 of a point under a grade. Mm-hmm. It makes it hard for me to sort of care about or put effort into that assignment. And so it's just so that if people have an opportunity, and it happens actually quite often, sort of people just go all in on that last assignment and sort of bumps them up a grade. And so that's just, I mean, it's also kind of accumulation of everything we've got up to this semester. So, I mean, I guess you could think about it as kind of like a final project type of thing, but that's kind of my rationale. It sucks to be left out in the cold if you know, hey, sort of things are already set in stone and there's nothing I can do sort of moving forward. And so that's why I have this last assignment worth double, just so people can sort of improve their grade and sort of not hurt them. So, okay. All right. So what we'll do is we'll have this, your current set working on right now, have that due Friday at noon. Okay. So make sure you have all relevant files to CJ Friday at noon. We'll go through, process those, get those back to you so that you have those as a reference to go through and use. We'll have this set due, say, Sunday at some point, sort of after finals are all over. So make sure that you sort of get it in by then. But again, sort of work together, sort of talk about strategy and approach. Let me know if you have questions. Hopefully, this set will get you kind of in position to have a sort of better headspace on some of these procedures. But always let CJ know if you're running into difficulties. Okay, CJ, anything to add here before we sign off and never see anybody ever again in Psych 5060 via Zoom?
I don't think so. I feel like I should have something good or powerful to say here.
Right? You should. Oh, boy. That's terrible. Right at the end. You stumbled right at the finish line and fell on your face.
I know, I joked.
Well, again, thank you, everybody. It's been, I don't know, I think pros and cons to doing this over Zoom. Definitely prefer to sort of be with you all in person, but sort of I think we made probably the best decision we could given sort of everything that's gone on. You all have been fantastic. I know it's hard to hang out and listen to me talk about statistics for 3 hours as a stretch over the course of the semester, but you guys have all been very, very good. Your work's been awesome. Keep up for this last push. Let us know if you have any questions, and it's just been great working with you all. Okay, so take a break, enjoy your evening, and remember, go through, and not just for this class, for all your grad classes, so to go through, make sure you're filling out those evals so that we have scores for that starts to become important for us as we're going to go up. It sort of looks pretty poor if we can't get our doctoral students, so like a handful of doctoral students, to fill out evals, and then that goes up the chain to administration. Like, what are you doing, Clap? You only had 8 people to wrangle. You managed to get 2. But make sure to do that for this and other classes. Otherwise, thank you again for a good semester, and we'll catch you if you have any questions. All right. All right. See you later.